Okay, here's a video about graphs and acceleration. You've seen position versus time graphs before. These graphs tell us how far away an object is from the selected point of origin, which you can select the point of origin at random, as long that just becomes a reference point, so that tells you how far away the object is at any given moment during its motion. Here is a position versus time graph. This object, it looks like, started 3 meters away from the point of origin, or the reference point, and then it traveled 3 meters in the first second, stayed at rest for 2 seconds, and then traveled 6 meters all the way down in the next 3 seconds. To find the velocity from a position versus time graph, you have to take the slope of the line at whatever point you're talking about. So say I'm talking at 2 seconds, the slope would be 0. Or if I'm looking at 4 seconds, the slope is 1, 2 over 1. It's a negative 2 meters per second. Negative just means that it's coming closer to the origin. Then we'll talk about velocity graphs. These graphs show a velocity, which is measured in meters per second on the y-axis, and time, measured in seconds, on the x-axis. They'll show us the velocity of an object at any given moment during its motion. So this is the velocity time graph of the position versus time graph we just looked at. So the velocity for the first few seconds was 2 meters per second, and then it dropped down to 0 meters per second, and then it sped back up again. Then if we look at velocity and position graphs together, we can see how they relate to each other. So this would be a position versus time graph, and this is velocity versus time. This has more rounded edges this time because in real life we don't just stop and go super quickly. It's kind of a more smooth transition. So if we look here, we start at 0 meters per second, and that's where we start. And we speed up to 2 meters per second in that first second. And then we keep going 2 meters per second. That's why that's flat there. And then we drop down to 0 meters per second right here at the tip of this, because you're just kind of hanging around 6 meters away from the origin. And then we're going to go down in velocity, or we're going to gain velocity, but in a negative direction rather, and back towards the origin, and that's what's happening there. Acceleration. A lot of people get really confused about acceleration, but it's a very, very simple concept. So we have position graphs, which tell us where things are. Velocity tells us how fast things are moving. Acceleration just tells us how fast velocity is changing. So a change in an object's velocity is what we call an acceleration. That is measured in meters per second per second. We can write that as m/s/s, or m over s squared, but we don't actually say meters per second squared. We say meters per second, because that helps illustrate the idea that we're looking at the change in the velocity, which is meters per second, every second. So how much does that meters per second value change each second? When we have constant velocity, which means that it moves with the same velocity for a period of time, the position versus time graph has a constant slope, or it's a linear slope, it's a straight line. The velocity versus time graph has a 0 slope, which means that it's a flat horizontal line because the velocity isn't changing. And the acceleration has it would be at 0 meters per second during those times that it's not changing its velocity. So for example, this would be the position at constant velocity. That is moving. That is a straight line. There's a straight line too. That constant velocity would be 0 though, and that's a straight line. So all 3 of those sections are moving at constant velocity. And then here, that would be a constant velocity because it goes 2 meters per second. It still goes 2 meters per second. It still goes 2 meters per second. And then it changes. Then it changes again. So anytime that you have a flat line on a velocity time graph, that's constant velocity. If we look at some more graphs, we have a stationary object, one that's not moving over time, and the velocity is 0, and obviously the change in velocity is 0. If we look at something that's moving with a constant velocity, we call that uniform motion. That'll have a straight line on position versus time graph, a flat line on velocity, and a 0 at acceleration. And a motion with constant acceleration has got kind of a curvy exponential looking graph on the position, a straight line on velocity because the velocity increases each time, and then the acceleration has a flat line there. This is the same kind of thing. We look at some of the graphs we had before here. We're changing from 0 to 2, so we go from 0 to 2 there. Then we drop back down to 0 acceleration because the velocity isn't changing up here. And then you can follow those graphs all the way down and see how those correspond. If we were to calculate acceleration, we just take the change in the velocity and divide it by the time taken to change the velocity. Fancier way to say that is the final velocity minus initial velocity divided by the time taken, or VF minus VI divided by T. So for example, we have a car stopped at a stoplight, which means its velocity is 0, and the light turns green and the car accelerates. It takes the car 5 seconds to accelerate to 30 meters per second as a velocity. So what was the car's acceleration? According to our word problem, the final velocity was 30 meters per second. The initial velocity was 0 meters per second, and it went from time 0 to time 5. So we would plug that into our equation here and say 30 minus 0 is 30. 5 minus 0 is 5. 30 divided by 5 is 6 meters per second per second. Notice the units here is 30 meters per second divided by 5 seconds. That's where we get the meters per second per second. Finally, when we're looking at motion maps, if you have a motion map that has arrows that are equal in length, that is a constant velocity. It's moving the same speed for that whole time. But if you have the vectors next to each other that have different sizes, that means that an acceleration has occurred or is occurring during those times. So in this case, it's speeding up because the velocity is getting larger. How do we know? Well, those vectors on a motion map represent velocity. So if there's a change in size of the vector, there's a change in velocity, which is the exact definition of acceleration.